Alrighty, so the Millikan oil drop experiment. So this is an experiment performed by Robert Millikan in 1909, although I think from what I heard from many people it was like 1913 when he finished publishing, am I right? Something like that? He determined the size of the charge on an electron, and in fact that was his main purpose, right? Was to determine the size of a charge on a single electron. What Millikan did was put a charge on a tiny drop of oil and measure how strong an applied electric field had to be in order to stop the oil drop from falling. And so he was able to work out the mass of the oil drop, and when he could calculate the force of gravity on one drop, he could then determine the electric charge that the drop must have. By varying the charge on different drops, he noticed that the charge was always a multiple of minus 1.6 times 10 to the minus 19. And that is key, and I don't know if you found that in your own research. Okay? But what he found was that all of the charges were multiples of that minus 1.6 times 10 to the minus 19. Now, I usually like to go and explain that a little bit. What do they mean by a multiple? Like, what are the multiples of 4? 4, 8, 12, 16, 20, 54, 96, 104, and so on, right? So what Millikan would have done is he would have made a note of all of these charges. My guess is that he probably graphed them and likely got data that kind of looked like that. And then when he found the slope of it, like if these were all, if you graphed 4, 8, 12, 16, 20, 54, and so on, you would get a line. And when you found the slope of it, what would the slope of said line be? If you were graphing this and these numbers, what would the slope be? The slope would be 4, wouldn't it? Because the line would sort of be going up by 4. Now, in that case there, if it was exact numbers like 4, 8, 12, it would be perfectly 4, wouldn't it? But Millikan didn't have numbers like that. He had weird ones like minus 1.6 times 10 to the minus 19, and minus 3.2 times 10 to the minus 19, and minus 3.6 times 10 to the minus 19, and minus 4.8, and so on. And would it have been perfectly minus 4.8? No, it might have been 4.75. He probably had to round. So it's that multiple thing. And then he likely took the slope of that graph into that, okay? But I want you to understand that he didn't just get, poof, out came this magical number that worked exactly perfect every time. Okay? He would have probably had to graph it, probably took the slope. Now, many of you know about the controversy. What did he do? Well, some of his data points were way out of whack, all over the place. And what did Millikan do? He ignored them, didn't he? And the question is really, is that okay? And what is your opinion? And I'm not going to get into it now. I just want you to tell me what you think later. Okay? So this meant that it was electrons carrying this unit charge. So this charge, this minus 1.6, is the absolute smallest value possible for the charge. Okay? If we were dealing with my 4s, the absolute smallest charge would be 4, because the numbers never go below that. The numbers never go below 4. In this case, the numbers never go below the value minus 1.6 times 10 to the minus 19 coulombs. Okay? Does that kind of fill in some gaps a little bit? Or you knew that already? Is anyone listening? All right, so here's his apparatus. Now, I just happen to have one. It's sitting back here all year. Right back here. Yep. No, it's not the same thing, but it is an actual high school Millikan apparatus. Now, years and years and years ago, that back computer room was actually like a teacher prep kind of storage room, and it was filled with cabinets, and there was old chemicals like mercury and a whole bunch of other unsafe stuff like compressed chlorine gas and stuff like that. It was a little bit scary when we cleaned it out. So when we cleaned it out, yeah, having compressed chlorine gas was a little bit of a surprise. Some lead, all sorts of dangerous stuff. When we cleaned it out, we found about 8 to 10 boxes of these had never been opened. of these? I have no idea. They were, my guess, they were brand new when the school was built, 1971. So we kept one because, well, actually I opened one up, and I had one of the old science teachers. We tried to get it going one day, and we couldn't. It didn't use oil droplets. It used these little sort of plastic kind of, they were like just the tiniest beads you can imagine. They were incredibly small. And we tried to get it going, we couldn't figure it out. The directions didn't make a lot of sense. So we just jumped it. Okay? But I kept one just to show people. So you would see this thing here is a little sort of magnetoscope. And the little clamp here has been busted off over the years, but it would just sort of clamp there. This is the actual chamber in here. You can see, I'll send it around. You can see that the plates are about 1 centimeter apart. And then they use this thing here, and it's now bust because someone has decided to take it out. Oh, let's pull it this way, you can see. You can see little markings on it. You can look at the light and see it. And then they would actually count. They would time how fast it was falling. So that would look up there. This little container here is where the plastic beads would be. This is a light, so you could actually see what was going on. And then this would hook up to the battery here, and you could adjust the polarity of the plate by doing this. And I thought there was a way you could actually turn it up or not. And then there's supposed to be a little spray bottle. All right, there it hooked up. I get this here. Oh, there was this thing right here. There was a little rubber kind of thing that you would squeeze, and it would force the little beads through there. But you can actually see the plates. You can see that they're not very far apart. So I'll send that around. I'll maybe start over here. You can have a look if you like. But that's what sort of the apparatus looks like. Okay? This picture you guys have probably seen, right? Or one similar to this? Okay, so this atomizer is really just sort of a spray bottle. And he sprayed these little dots in here, right? And they fell through here, and gravity, wait for us, gravity would pull them down, and it would be hooked up to a battery, right? You guys know all this already. Okay, so an atomizer sprayed a fine mist of oil droplets into the chamber. Some of these tiny droplets fell through a hole in the upper floor. Millikan first let them fall until they reached terminal velocity. Using the microscope, he measured their terminal velocity, and by use of a formula, calculated the mass of each oil droplet. And one of the other things that people believe he made a mistake was had to do with the viscosity of air, I think. Am I right? Something like that? Right? The viscosity means like how thick it is. Okay, you talk about oil viscosity. When it's cold like this, the viscosity of oil goes down. It gets really thick, kind of like a milkshake. And when it heats up, then it's nice and sort of fluid. Next, Millikan applied a charge to the falling droplets by illuminating the bottom chamber with X-rays. So he zapped them with an X-ray. Now, in that apparatus there, just the friction alone would give them enough charge, just by friction being pushed through the plastic. This caused the air to become ionized and electrons to attach themselves to the oil droplets. What is an ion? Remember from grade 9 science? What's an ion? You're right, Colin, go ahead. Has positive or negative charge, right? So like when lithium, right, is +1, which means it's actually losing electrons. When lithium loses an electron, it becomes a lithium ion, positive charge. Pardon me? Same idea, yeah? It's giving off electrons, right? Yeah. Okay, so the air became ionized and electrons to attach themselves to oil droplets. By attaching a battery to the plates above and below this bottom chamber, he was able to apply an electric voltage. The electric field, which is what this unit is all about, produced in the bottom chamber by this voltage would act on the charged oil droplets. If the voltage was just right, the electromagnetic force would just balance the force of gravity in a drop, and the drop would hang suspended in midair. Now, you're going to see this diagram many times in the next couple weeks. Weight force, gravity was pulling the oil droplet down, and the electric field, much like a gravitational field can pull, right? But electric fields can pull, but they can also push. And so this electric force, due to the electric field, was up. And the more battery power he added, the greater the electric field, which means the greater electric force. And if he played his cards right, he could get those two, give me a second, Colin. He could get those two forces balanced, equal, Riley. Equal. And if he knew the mass, and he knows gravity, right? If mass times gravity would give you the weight force, then that would be equal to the Fe. And I haven't told you this yet, but the electric force is QE, where E is the electric field strength, and that's how he figured out the value of Q, which is the charge on the oil droplet. That's a lot of steps, right? That's a lot of steps. Colin.
Oh, like, I know it's not possible, but create a zero gravity chamber that just uses electromagnetic field.
If you as a human were charged and they create an electric field, yes, that's theoretically possible. I mean, it's basically the same idea as when they have those indoor sort of ones, right? So basically, you're the person, there's weight, force, gravity, and on the bottom here, they got that big fan blowing, right? And the air is up, right? So it's the same idea. You've got an air force, I guess, an applied force. Same idea. Okay, so it says here, now you try, click here to open a simulation of Millikan's chamber. First, allow the drops to fall. How many people were pretty successful at finding a simulation? It's a bit of a challenge. It's a little easier at home, maybe where your computer is up to date and there's not all some kind of security settings. I had some trouble too. Okay, I think I've got one here. I'm just going to watch this one here. Okay, is it going to work today? Or are they going to block me? Here we go. Some of you may have actually seen this one. Now, if I had more time, I may. Oh, did you actually? Oh, I see. You could actually maybe do this, but okay. So that's what it kind of looks like. If you guys look through the little microscope thingy, it kind of looks like this, right? And you would spray that in there, and then you turn the voltage on, and you should be able to adjust the voltage. Oh, X-ray on. Should be able to see, and then he would have done this, and he would have been able to get the oil droplet to balance, right? And knowing the mass, because he found the terminal velocity, knowing the mass. Oh, now why is that one falling? Those other two are standing there. It's heavier, and the electric force is based on, right? It has more mass, exactly. So he had to find a certain drop that he liked, that he could find the mass of, and he had to keep track of it too, right? Because if it's falling, he's got to keep track of it, and then he's got to turn the voltage up and keep track of it and find it. That same one, right? It's not going to like flash and say, yeah, that was me. Remember, this is all 100 years ago, right? So it's kind of amazing that he could actually do that. Okay. So this next part here is talking about that same stuff that I've talked about. Let's look at the calculation Millikan was now able to do. When a drop is suspended its weight, mg is exactly equal to the electric force QE. The values of E, the applied electric field, the m, the mass of the drop, and the g, the acceleration due to gravity, are all known values. So you can solve for Q, the charge on the drop. Millikan determined the charge on a drop. He redid the experiment numerous times. How many times? How much data did you come up with? You know? Lots. How many drops did you throw away? I think it was over 100, I think, wasn't it? Yeah. Can I finish here? He redid the experiment numerous times, each time varying the strength of the X-rays ionizing the air so that different number of electrons would jump onto the oil molecules each time. He obtained various values for Q. And this is key here. This is key. The charge Q on a drop was always a multiple of minus 1.6 times 10 to the minus 19. It's like that 4, 8, 12, 16, 24, 96, 100 stuff I was talking about. Right? This number was the one Millikan was looking for, and it also showed that the value was quantized. Quantized. Anyone Google that up? What does quantized mean? It means it's indivisible. You can't break it down anymore. When you buy eggs, right? You buy eggs at Co-op. What do they come in? Packages of? I think you can buy 6s.
Yeah.
Maybe not at Co-op, but someplace. You can buy 6s. You can buy 12s. You can buy 18s. Can you buy 24s? I think you can. Maybe it's a flat, right?
Yeah, there's.
But there is a smallest number of eggs you can buy. It is 1. Or you can get, right? You can only break down eggs to the smallest part of the possible thing, which is 1 single egg. That's what quantize means. Okay? Yeah. Okay. Now, I got a couple things that I'm going to zoom through because we missed a day, but I'm going to show you this video because it's really fun. One of the controversies is that Millikan had, a lot of people believe Millikan had his number in mind. His number was minus 1.6 times 10 to the minus 6. Right? Did he not have a rival?
Yeah.
There was another guy that was trying to find the same thing, and he had a different number in mind, right? So a lot of people believe that Millikan threw away that data because it pushed his number closer to his rivals. He was trying to find data that proved he was right. Is that the right thing that scientists should do?
No.
In fact, they should look for things that
Prove
them wrong. Right? And so they can change their way of thinking a little bit. Okay? Now, if you've seen this video, please keep it to yourself. It's not long. Okay, let's begin. So I need your attention here. We're going to do the old highlight thing again. What's the difference between this and what? Quantum physics? Quantum physics is all about sort of the inner workings of the atom. A little more advanced over here. Okay? There's what? Oh yeah, proton, neutron, yeah, and they break down too. We sort of lie about that stuff too. Lies, all lies. Okay. Anyways, let's begin, please. Quantum physics, my friend. Another time. Okay, ladies over here. I need you guys to pay attention. The space around a strong magnet is different from how it would be if the magnet were not there. Put a paperclip in the space and you'll see the paperclip move. The space around a black hole is different from how it would be if the black hole were not there. Put yourself in that space and it'll be the last thing you do. Similarly, the space around a concentration of electric charge is different from how it would be if the charge were not there. If you walk by a charged dome of an electrostatic machine, a Van der Graaf generator, right behind Riley there, you know what, I got to check the belt. You can sense the charge. Hair on your body stands out, not so much for me. Just a tiny bit if you're more than a meter away and more if you're closer. The space that surrounds each of these things. Colin, I'm doing the teaching part here. The magnet, the black hole, and the electric charge is altered. The space is said to contain a force field. A force field. Can you see said field? No. You can only see it by if you put an object in and you interact with it. We can't see the Earth's gravitational field. We only see it when we drop something. Right? We observe it. You're right, it's not seeing it. We observe its action, I guess you could say, right? Okay, so this is your introduction to electric fields. We talked about Millikan, but I haven't really talked about what is an electric field. So bear with me, please. The force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it curves because there is an interaction between the ball and the earth, between their centers of gravity to be exact, and their centers of gravity are quite far apart. So this is, again, action at a distance, or if you will, force at a distance, right? You're applying a force even though there is no connection. There is this ability to apply a force even though they're not physically in contact. The idea that things not in contact could exert forces on one another bothered Isaac Newton and many others. The concept of a force field eliminates the distance factor. So we came up with this concept of a force field. The ball is in contact with the field all the time, and I talked about this when we did gravitational fields, right? Here's the Earth's gravitational field, right? And there's the object. It is touching the force field. Not touching the Earth, but touching the force field. We say that the ball occurs because it interacts with the Earth's gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the masses of the Earth and other astronomical bodies that are responsible for the fields. Just as the space around the Earth and every mass is filled with a gravitational field, the space around every electric charge is filled with an electric field. So where do electric fields occur? No. Space around electric charges. Right? Space around electric charges is filled with an electric field, a kind of aura that extends through space. In figure 33.2, a gravitational force holds a satellite in orbit about a planet, and an electrical force holds an electron in orbit around a proton. In both cases, there is no contact between the object and the forces, again, acting at a distance. Okay, so there's the diagrams there, right? Both of these are, the satellite is in contact with the gravitational field. The electron is in contact with the electric field. And they are all virtually identical in that they extend outwards, they follow the inverse square law, they get weaker as you move away, the density of the lines determines the strength, all that stuff. Okay? In other words, the force that one electric charge exerts on another can be described as the interaction between one charge and the electric field set up by the other. So every object that has a charge has an electric field, just as every mass has its own gravitational field. An electric field has both magnitude and direction. What does that mean? It means it's a vector. Well done. It's one of the other vector quantities. Its magnitude or strength can be measured by its effect on charges located in the field. Imagine a small positive test charge that is placed in an electric field. Where the force is greatest on the test charge, the field is strongest. Where the force on the test charge is weak, the field is small. Now this little star here is the footnote where it says the strength of electric field is a measure of how great a force will be exerted on a small test charge placed in the field. The test charge must be small enough that it doesn't push the original test charge around, or the original charge around, and thus alter the field we're trying to measure. If a test charge Q experiences a force F at some point in space, then the electric field at that point is E equals F over Q. So in other words, you have to use a really tiny charge to measure the electric field, and it has to be so small that it doesn't affect the other one. Okay, it's like using a ping pong ball to measure the Earth's gravitational field. It's really small. Now, this is important here. Star beside this. The direction of the electric field at any point, by convention, is the direction of an electric force on a small positive test charge placed at that point. We use the charge positive to test the direction, because gravitational fields can only do what? Pull, but electric fields can pull and also push, depending on the charge, right? So we have to decide, how are we going to measure it? Just like we say that red lights mean stop, and we drive on the right-hand side of the road, by convention we use positive test charge. Could we all decide tomorrow to use negative test charges? We sure could. Could we get everyone in the world to agree to that? No chance at all. Okay. So someone, somewhere along the line, came up with positive test charge, and everyone else just decided that was a good idea. If the charge that sets up the field is negative, thus if the charge that sets up the field is positive, the field points away from that charge. If the charge that sets up the field is negative, the field points toward that charge. Be sure to distinguish between the hypothetical small test charge and the charge that sets up the field. And I will be coming back to that again and again, as I always do. Cycle back. That's your first review of that. Okay, now what about these electric field lines? Now, I didn't spend a lot of time with you in gravitational field on this, but I'm going to spend some time now. Since an electric field has both magnitude and direction, it is a vector quantity and can be represented by vectors. The negatively charged particle in figure 33-3 top, that's this one over here. So see the negative charge right there? Okay. The negatively charged particle is surrounded by vectors that point toward the particle. If the particle were positively charged, the vectors would point away. So why are all these arrows pointing towards it? Because it's negative, and we use a positive test charge, right? The vectors always point in the direction of the force that would act on a positive test charge. The magnitude of the field is indicated by the length of the vectors. Whoa, Mr. Bennett. The length of the vectors. That's not what you've been telling me already, right? Let me explain. The magnitude of the field is indicated by the length of the vectors. The electric field is greater where the vectors are long than where the vectors are short. Where are these vectors long? Closer together, right? And as you go farther away, they get smaller and smaller. Like way out here, they'd be almost invisible. But real and tight here, they would be longer. In fact, they'd be so long, they would actually be past the original one. In fact, if I drew vector for every point in space, what would it look like? In fact, it would be more than that. It would, in fact, be it would be literally black. Complete and utter. Every spot would be filled in, right? Every vector would be drawn from every point. Does that make sense? Is that a usable diagram? No, that's called a black square. Useless, right? To represent a complete electric field by vectors, you would have to show a vector at every point in space around the charge. Such a diagram would be totally unreadable. It'd be nothing but a big black blob. So we do not use vectors. A more useful way to describe an electric field is with electric field lines. Is this also true for gravitational fields? If I drew a vector from every point around the Earth, big giant black, yeah, exactly. So a more useful way to describe an electric field is with electric field lines, also called lines of force. Where the lines are farther apart, the field is weaker. You guys know that already. For an isolated charge, the lines extend to infinity, while for two or more opposite charges, the lines emanate from a positive charge, terminate on a negative charge. Some electric field configurations are shown here. Let me just announce that. I'm going to show you this. Okay, so this one here. Now, why in this case, up here, how come the lines are pointing? These are not vectors, field lines, because it's negative. How come this one, they're away? Because it's positive. So gravitational has to be towards, but electric could be towards or away, and it depends on the charge of the object. These ones here go from positive to negative. Does that make sense? If you were to put a small positive test charge right there, it would go woo like that. It would make that sound too. Right? So away from positive and towards negative. If you've got two charged plates, like in the Millikan apparatus, we go from positive to negative.
Wait, isn't that diagram of B, isn't that the same thing as a magnet?
It's exactly the same as a magnet. That's just like a North Pole, South Pole kind of relationship, isn't it, Riley? Yep, absolutely. Photographs of field patterns are shown in figure 33.5. The photographs show bits of thread that are suspended in an oil bath surrounded by charged conductors. The ends of the bits of thread are charged by induction and tend to line up end to end with the field lines like iron filings in a magnetic field, just like my friend Riley said. Notice that between the plates, the threads are aligned parallel to each other. The field has a constant strength between the plates. Also notice the threads inside the cylinder are unaligned. There is no electric field in space inside a conductor. The conductor shields the space from the field outside. That, my friends, is sort of, anybody ever heard of a Faraday cage? Okay. Faraday cage is why your cell phone doesn't work in the rotary arena. The rotary arena is a big metal building. It's a Faraday cage. It has a charge. Okay, it has a small electric charge and it has an electric field, and it doesn't allow electric transmission cell phones to sort of penetrate it very well. If you've anybody ever watched the TV series Lost from way back when, they talk about Faraday cages in there. There was one recently where maybe it was on Big Bang Theory. They were talking about a Faraday cage, and I went, "Yeah, sorry, I know what that means." So now you do too. It basically is a electric field that sort of shields you. Okay, so yeah, I mean, there's a lot of factors, right? I mean, I've really simplified it. So here we have, these are actual electric fields. Can you tell which one of these is positive and which one is negative?
Yeah.
And this first one here? You can you tell me that they are both the same, or can you tell me that they're both opposite? How do you know that these are opposite? Because they connect, right? So like one could be positive and one could be negative, or it could be the opposite way, right? Should have went with red. We don't know which one is which. What about this one here? They're the same? How do you know? Yeah, because they don't connect. They kind of push away, right? So they're both negative or both positive. We got two charged plates down here, it looks like. Okay, this is what they're talking about. This is the Faraday cage. there's no lines, right? It's just sort of all random. It's all jumbled up. Faraday cage. No electric field inside. I think it was on that show Timeless. Anybody ever seen that show, the time traveling thing? I think that's where they talked about a Faraday cage. Can't remember. Okay. If our only concern for electrical forces were limited to isolated point charges, the electric field concept would be of limited use. The force between point charges is adequately described by Coulomb's law, something that I used to teach in grade 12. Charges most often are spread out over a wide variety of surfaces. Charges also move. When charges move, we call that electricity. This motion is communicated to neighboring charges by changing the electric field that emanate at the speed of light. As later chapters will show, the electric field is a storehouse of energy. The energy can be transported over long distances by an electric field, which may be directed through and guided by metal wires or directed through empty space. Okay, now there's a bit of a sort of a summary here if you want, sort of the key points that you might want to sort of highlight. There are some questions here that you can sort of try, and I'm going to ask you go. You actually have a fair bit of time. You can try those. Just to sort of make sure you understand what's going on. But first, let's talk about this one thing here in the corner here. See what it says question? And then I'll be quiet. Question. Suppose that a beam of electrons is produced at one end of a glass tube and lights up a phosphorus screen on the inner surface of the other end. So I'm going to draw a electron gun. Okay? And it's produced at one end of a glass tube, lights up a phosphorus screen on the inner surface of the other end. So we've got this glass screen over here, and it's coated in phosphor. And phosphor will glow when it's struck by an electron. Okay? When the beam is straight, it produces a spot of light on the middle of the screen. If the beam passes through an electric field of a pair of oppositely charged plates, so if I put some plates here and I make this positive and I make this negative, right? The beam passes through the electric field of a pair of opposite plates, it is deflected, say to the left, or in this case, my drawing here, let's say it's deflected up. And so now my point on the screen is there. And if the charge of the plates were reversed, in what direction would the deflection occur? In other words, if I change these to negative here and positive down here, well, then my electron beam would go that way. Now, who cares about stuff like this? Scientists? Well, about 15 years ago, I could say you should all care because you all have one of these in your home. I'm guessing that very few of you have these in your home anymore. You might see one at Grandma's house, maybe. Close, but you're on the right ballpark track.
Big TV antennas.
No, but you're getting really close. Those old school TVs, you know, the big tube TVs, the big box TVs? Who still has Grandma and has one of those at home? No one? No. You guys ever seen one of those? Yeah, in the basement. We used to have a big 32-inch one. 32 inches cost me $1,000. Yeah, for one of those big tube ones, right? So what these old school, if you've ever seen one, when they sort of start to wear out, when you turn the power off, what happens? You ever seen that? It just sort of goes, so the picture kind of goes down to a dot, right?
Yep.
What's happening is the electron beam. Each and every one of these is in one of those old school TVs. So that you could watch that show on those old school TVs, this electron gun would fire out, and the electric plates would use an electric field, and it would force that beam to go back and forth on the screen, back and forth like this, but it would do it really, 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 really fast, right? And it would jump over plates. You ever look at one of those old TV screens really, really, really close? What does it look like? It flickers, but if you look really close at the screen, you'll see the three primary colors. And with those three primary colors, depending on where the electrons would exactly clip, right? You could get any color you wanted. And because it was doing it so fast, what was it doing? Creating a color picture. Okay? They couldn't get color TVs until they could figure out a way to change that electric field fast enough. And by doing that, they could go into three different colors. They could shoot this electron beam and hit all those colors, and it's going so fast your eye couldn't see it move, right? And then when you power off, the electric field disappears, and the electron gun just points right in the center. So that's how those old TVs used to work. Don't ask me how LCD TVs work. I don't know. Kind of know dinosaur. All right, I'll be quiet. You guys have done well. You've listened to me pretty good here. So there are a few questions there. I sort of expect you to know the answers to these. Should I go through them maybe at some point?
No.
Probably, right? So how about, I say you got about 20 minutes here. You probably can't get them all done. You can certainly read them, and then maybe first thing Monday morning I'll zip through the answers quick. Okay?
You know, the first